Hello, ladies and gentlemen, and thank you for standing by. Welcome to this ASM webinar on how effective is 2D DIC in materials testing. I'm Joanne Miller, Senior Editor with ASM International, and we're glad you could join us. Today's presentation is part of the ASM webinar series designed to provide information that you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. The series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsor of today's webinar is DIC Software. DIC Software is one of the world's leading suppliers of material and component testing systems. The company supplies both standard and tailor-made solutions for the most demanding requirements in R&D production and quality assurance across more than 20 industry sectors. Privately held, the company's consistent focus on innovation and commitment to outstanding quality have supported its growth in markets worldwide. Additional information about DIC Software may be found online at dicsoftware.com. We're proud to have DIC Software on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the GoToWebinar session, dial 877-582-7011. All participants will be in a listen-only mode during the presentation. Feel free to submit written questions at any time by using the Q&A window located in the upper right corner of your screen. Click the question mark button to open the Q&A window, type your question in the box, and click the send button. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. We are happy to announce that registration for AeroMat 2021 and ITSC 2021 is now open. While we were looking forward to seeing everyone in person at this co-located event, the safety and well-being of our attendees and exhibitors is our top priority. As a result, both events are now pivoting to a 100% virtual conference and expo platform. Get on-demand access to technical presentations and engage and interact with your colleagues from around the world. For more information and to register, visit aeromatevent.org or itscevent.org. With that, I'd like to introduce the instructor of today's webinar, Fadi Abu Farah. Fadi is currently operating a startup, Fadi AMT LLC, focused on the advanced characterization of a wide range of materials with the aid of optical metrology, particularly using digital image correlation, referred to as DIC. Fadi received his PhD in mechanical engineering from the University of Kentucky in 2007. After that, Fadi was an assistant associate professor of mechanical and automotive engineering at Penn State University and Clemson University's International Center for Automotive Research. Fadi's primary area of research was lightweight materials and their manufacturing. He received several Best Poster and Paper awards at multiple events, including NAMRI SME and TMS, and won the Young Researcher Fellowship at the 3rd MIT Conference on Computational Fluid and Solid Mechanics. Fadi is a recipient of the NSF Career Award, the SME Young Manufacturing Engineering Award, and the SAE Ralph Teeter Award, and the TMS Light Metals Division Award. It is a pleasure for me to introduce Fadi.
Thank you, Joanne. Good morning, everyone in North America, and good afternoon or evening for those in Europe or the East. Thank you so much for attending this webinar on the effectiveness of 2D DIC in material testing. I would like to start with a very quick introduction to ourselves. So we are a material testing lab in South Carolina. We've been operating for about 6 years. And I would like to mention just a few things about us in terms of what we focus on in material testing and component testing. First, we focus on state-of-the-art facilities, bringing the best that's out there in order to characterize materials, and we combine it with highly skilled personnel. And the second item is we try to integrate optical metrology and digital image correlation in particular with most of our testing so that we can extract more out of what we test. And ultimately, we try to elevate the outcome of what we do in terms of testing, and we stretch the limits to go into customized and non-standard tests in the field. What we perform is really a wide variety of tests, as you can see on the screen, with different types of loading conditions for different materials. Maybe automotive is our main focus, but we do also perform tests for other fields. And I usually like to show a very quick video that highlights the kind of work that we do. And I know that I probably showed this video before, but it's such a nice example of what we do. It's a bulge test for a 4-micron foil with digital image correlation to show characterizing the material behavior, capturing really low signals of pressure, and also integrating all of that together in a single test. This is just a quick snapshot of our partners and customers from around the world. And with that, I would like to go to my webinar today. And from the title, how effective is 2D DIC in material testing? Of course, we want to evaluate the effectiveness of 2D DIC, but in essence, what we're trying to do is also provide a comparison with 3D DIC in material testing. So let's start with a very quick introduction about digital image correlation. Even though most people nowadays are familiar with it, I would like to define it from a material testing perspective or aspect, and I would like to focus on tension testing. This is a typical tension setup, and you can see here we're showing a 3D DIC, a commercial DIC, monitoring a tension sample during testing. So what DIC is basically taking digital images of the sample during deformation, with one of them being the reference image, and dividing that image into basically subsets or regions of a certain number of pixels. Each one of those regions is called a subset or a facet, depending on the software that you use. And then from there, we take each one of those regions of interest and track their movement and distortion as a function of time, as the material is deforming. And by tracking the center of each one of those subsets, we can establish the deformation vector field by combining all of these subsets together. And from that, we can compute the amount of plastic strain that was experienced by the material, and thus generate a strain map, such as the strain map that you can see here on the right-hand side. So maybe a closer look at a stress strain curve. If I were to take just 2 points to draw this example, the beginning of the test where I took an image, and then somewhere close to the end of the test where I took another image at that location. And just to demonstrate what each one of those subsets means, I try to actually zoom on the same location at the beginning of the test and the end of the test, so you can see what kind of movement and stretching happened in that subset. And to some extent, you can see the square subset became a rectangular subset, which is a representation of what happened during this tension test. And that is a positive strain in the y direction and a negative strain in the x direction. And once this is compiled for the entire sample, now we have the information that leads us to these beautiful color maps that we are used to seeing from the IC. And that color map represents basically that deformation in the material. So DIC examples are out there, but I usually like to show a video of what DIC gives us. Usually it's a strain measurement technique, which means you are focusing on strains, but that doesn't mean that you cannot combine it with forces or stresses so that you can construct meaningful engineering curves that we are used to, such as the engineering stress strain curve here or shear stress strain curve in some other scenarios. So a video like this highlights the power of DIC. You not only get the colorful maps that show you the deformation of the material, but also engineering values such as plastic strains to failure. Applications of DIC are of course limitless, and I've shown this in previous webinars that DIC truly transforms the way we characterize material deformation and failure. So there is no limit to what applications you can use DIC in. But then there are some obstacles or hurdles with DIC. One of them is typically the price. It is sometimes portrayed as an expensive system for what it is. And I put there a star because it's all relative. To some extent, this feeling that DIC systems are expensive is typically coupled with this second problem, that the majority of the time, DIC is used in support of tension testing. And so if you just take it from that perspective, of course, obviously, it looks like DIC is really expensive for what it provides, because I did say this also in a previous presentation or a webinar, that you can absolutely construct the same stress strain curve with the same accuracy using a conventional extensometer. So why use DIC? So with all these hurdles, there's still some positivity out there. And the first one is I still go back and insist on saying that DIC really enriches the amount and the type of data that we get from testing. So even though you can, to some extent, construct the same stress strain curves in a tension test, that doesn't mean that you shouldn't use DIC or consider using it, because the quality of the data that you get is, again, transformative. Second, there are so many people who still would like to access DIC and integrate in their testing, but there are some limitations. The cost is one of them, and the justification behind such systems. And third, nowadays we have lots of resources out there. We have lots of DIC softwares that are available for users. The cameras are more available to users who want to use basically digital image correlation. So with all these positivities out there, the question is, why not use DIC? And also, why not start with 2D DIC? So let's talk about 2D DIC and see where can we use it and how. So 2D DIC is clearly shown in this schematic. The main difference between 2D and 3D DIC is basically the number of cameras that you're using. 2D DIC relies on one single camera, and therefore it's typically limited to planar fields of deformation, while 3D DIC uses 2 or more cameras. Thus, we have a depth information so that we have the coordinates in 3D space for every single point of deformation, and thus we can use it for in-plane and out-of-plane as well. So the question here, when we take a closer look at 2D DIC is, or a set of questions is, how good is a 2D DIC strain measurement? And to define good, we're talking about the accuracy and reliability of that measurement. And then a follow-up to that is, if I have a measurement from 2D DIC and it's not showing, let's say, the accuracy or reliability that I am expecting when I compare it to a 3D DIC, how does that affect my outcome of the test? And we will explain that later on in the webinar. And third, if I have a 2D DIC system and I can prove that the outcome is really good and the data is reliable and accurate, what can I use it for other than the conventional tension test that everyone knows about? So this webinar tries to address these questions and others by performing a direct quantitative comparison between 2D and 3D DIC measurements in a series of tests that are real, practical, industrial tests that are used by the industry to generate data that we use every day, and at the same time covering several applications in the industry. The objective here is to provide the data, to provide you with the technical data, not just general comparative data by just saying 2D DIC is good for planar and 3D is good for out of plane. No, give you the quantitative technical data to support the general statement that we can still do a lot with 2D DIC without compromising quality. And so that's the objective of the webinar today. And so hopefully we can prove that today. And our approach is to do a comprehensive experimental study on selected in-plane experiments. And to do that, we are considering certain parameters. The first one is we will consider several test types. And to mention here, of course, we will start with the tension test of standard samples. This is the workhorse of the industry that is used almost every day, the 6892 standard. And then we will diverge from that to other types of tension tests, such as subsized samples or oversized samples that are used typically in crash simulations or fracture model calibration in crash simulations. Then we will go to some other special tests, such as the plane strain tests, the notch tension test, shear test, and others. So we will try to cover as many tests as possible to show the applications of DIC, especially in a 2D mode here. And to do that, we are coupling different types of systems together in a unique experiment. We will couple or combine 3D DIC system, a commercial full 3D DIC system that is capable of doing multiple volumes or multiple measurement volumes. A second system is a 2D DIC system, also configured in a similar way to have multiple measurement volumes, so it has the flexibility, just like the 3D DIC system. And then also a third variant, which is a 2D DIC system that is based on a commercial product, like a video extensometer or a laser extensometer, because this is a very important option for those out there who already have such sensors. They have an extensometer, which already has some cameras integrated in it. And so that's why we wanted to consider this one here, but we focus on one particular measurement volume here for one particular comparative experiment. So apart from covering different experiments and different DIC systems, we also covered multiple materials because we wanted to investigate whether the results that we are getting are really sensitive to the material and its ductility and strength and so on. So we're going to use some high strength steel, some low strength steels with extreme ductility, and also some aluminum alloys, just to diversify our materials. So these are the parameters that we're considering. There are so many other parameters that we are considering, and we're trying to keep the same when we test the different materials and different DIC systems. So we're trying to keep the measurement volume or the measurement area as close as possible when we consider the 3D DIC systems. We will try to match the pixel resolution as much as possible. We will unify lighting, and also we will unify the DIC processing parameters so that we can get meaningful comparison. On the other hand, we still played a little bit with some parameters and we kept them different intentionally. So you will see in one of those scenarios, we will not use speckle patterns. We will just use the natural contrast of the sample itself. We did consider the same side of the sample and then two different sides of the same sample. And also we considered different DIC processing softwares and different camera angles with respect to the sample. So you can see we have a very, very wide variety of parameters, which is, of course, obviously I cannot cover them in today's webinar, but we decided to show you some of the highlights of these experiments today so that we can convey the message. So let's go to the experimental setup. This is our setup, and I know it's crowded, but we wanted to start with a clean image of what is there because we did combine a lot of things together. You will see here that there are three DIC systems with a tension machine, multiple softwares, multiple computers, so that we can gather the information from all these systems and then couple it together seamlessly. And to just show you the details of this setup, if this is the test sample, that small thing inside the yellow box, we started with a 3D DIC system that I highlighted here in white, and you can see the two cameras pointing at the test sample at certain angle. Then we have our 2D DIC system, a single camera with a single lens, and also looking straight at the sample from the same surface or the same side. So we're measuring the same exact surface with the two systems here. And then we have a third system that sits in the back, which is the second DIC system. It's a 2D system with a special lens that I will explain in a second. but it's basically intended to do the same measurement on the same test sample from the back side of the sample. Let's go into the details of the systems. We try to match, like I said, the parameters as much as possible. So for our 3D DIC system, we borrowed a 12M system. Basically, this is a commercial product with two 12-megapixel cameras. This is some of the highest resolution cameras that you can find on the market, which is plenty enough. We coupled it with 75mm lenses so that we can back off the system a little bit to the back so that we can fit the other system in front of it. And we used it in a vertical orientation so that we can maximize pixel resolution. We set the camera angle to 25mm. And in terms of measurement volume, as I mentioned earlier, this was a flexible system, so you can set it up to a small or large volumes. But just as an example here, when we focused it on the ISO type sample, which is the standard sample, we achieved a pixel resolution of around 30 microns per pixel. For processing, we used a full commercial software, which is the GOM Correlate Professional software. And in this presentation, I will be showing the results for this system with that label that is down there, 3D DIC in black. The second system is our 2D DIC system, which is a single camera. And again, to try to match the 3D DIC system as much as possible, we used a comparable camera. It's also 12 megapixels. We coupled it with a 50mm lens. And we also used it in a vertical orientation so that we can maximize pixel resolution. We were able to achieve the same pixel resolution for the standard sample, which is around 30 microns per pixel. And so that will make the comparison really meaningful as we go to the results. And there is the software we used is the 2D version of the GOM software, or basically the GOM Correlate, which is exactly the same software with less features, so that we can just show what you can do with systems like this. And the results will be shown in orange as shown in the lower label. Finally, for the second 2D DIC system, we are using a video extents by DIC, which comes with a nice telecentric lens, as shown here. This is the large rectangular box in light blue in my picture. And this telecentric lens is selected to give an ideal field of view for one particular test, which is the standard tension test per ISO 6892. And that's what we're going to focus the comparison between this DIC system and the other systems. This telecentric lens gives us a nice field of view that covers this sample size. The camera for this system is a little bit lower resolution, but it's still fantastic resolution, 6 megapixels. And therefore, you can see my pixel resolution for the measurement was around 40 microns per pixel, which is still very comparable to the other two systems. And the difference is really insignificant. For this particular system, we will use this label, which is 2D DIC in blue. And one other detail that we must mention here is that for this particular system, which is usually looking at the backside of the sample, we did not use any speckle pattern. Rather, we relied on the DIC module, which is also provided by DIC, which is a separate module within Test Expert that allows you to process the images in a DIC software. So let's go to the experiments. And I would like to go through the tension testing experiment, maybe a little bit more detail, because this is our primary comparison, and then maybe we will go a little bit faster with the other examples. But we will try to focus on the tension testing and show how the results compare between the DIC systems. So this is a schematic of the sample that we are talking about, which I think everyone is familiar with it. This is the standard of the industry, and it's used to generate strains with a 50mm extensometer. So just a little bit of details before we show the results. After setting up the DIC systems, as I mentioned earlier, we even try to match the processing parameters so that we can have a valid comparison between the systems. And here, this is a snapshot of the 3D DIC software and the 2D DIC software, showing here that the field of view of the cameras are very comparable, and that's the vertical length of the picture or the image. And second, in terms of the processing parameters, we try to select the processing parameters, particularly the overlap between the facets, so that we generate the same reference length. And what reference length means here, in a simple way, is the equivalent mesh size. If this was to be done in a finite element domain, if you're doing a finite element simulation of this kind of a test, you would use a mesh. The finer the mesh, the higher the resolution and the more computational. And so it's the same thing here. And we use this reference length to always match our experiments to finite element simulations. And what matters here is that this reference length, by matching it between the different DIC systems, we are guaranteeing a fair comparison for the results in terms of the resolution of the result. The same thing we did even with the third DIC system, even though it's a totally different software, but you can still do it because it's just a matter of finding the right parameters and matching the parameters. And as you can see here with the DIC software, you can see a mesh, again, a grid, just like a finite element grid. And we try to match the grid in order to obtain the same pixel resolution and at the same time the reference length. Let's see a comparison of the results. This is for the aluminum alloy, and we are showing here the final strain map right before fracture for all 3 DIC systems. And I know it's a lot to digest with so many labels put out there, but I would like to start with a very simple comparison globally. Globally speaking, you can see that we are seeing very similar deformation strain maps between the 3D DIC system and the 2D DIC system in orange, simply because they were looking at the same surface up front, and you can see almost a match in terms of the localization. And if you can read the labels, you will see almost a match in terms of the global strains. As for the other system, which was in the back, you can see like a flip, a mirror image of it, because it was looking at the back surface. Now, the contrast pattern looks a little bit different just because of the software visualization. But if we take a closer look at the properties that we are reading or the strains that we are reading, I summarize those numbers to you so that it's easier to read in this table. And you can see the nominal strain, which is the 50 millimeter gauge length strain, that's the nominal Y strain, is almost exactly the same in all 3 systems. We're reading about 27.5 plus minus a small amount between the 3D DIC system and the other 2D DIC systems. And that should be the case if everything is done properly. We should see very small difference between them because we matched almost everything and the deformation is planar. And so we shouldn't see much deviations between them. When we compare the X strains, which are the transverse strains, we see a little bit more deviation there only in the last frame. And that also makes some sense because the X strains, the sensitivity there is much higher because you have necking within the sample where you're measuring the strains. And that's where you will see differences between the 2D and 3D DIC systems. Question is, how significant is this deviation? So now we see these numbers. Can we put this into perspective? Who can decide whether these results are good enough or not good enough? Who can decide whether this deviation in the minor strains, which is the negative, is large enough to say, okay, we cannot use the DIC? So to do this, you must go back to the outcome of the test. And the outcome of these tests is typically a stress strain curve. And we plotted the stress strain curves here on top of each other for the 3 systems. And as you can see, they are indistinguishable, which means if you're trying to extract stress strain curves from the systems, they will look exactly the same. If I go to the true stress strain curve for those who want to do finite element simulations, you will see also a match. So if my outcome is stress strain curves, whether engineering or true, I'm seeing a match. So I am not seeing any effect of the deviation of the minor strains. Then let's go to the next one, which is the R value. This is where we should see a significant difference, but we don't see it because the final comparison of the minor strains is a little bit deceptive. It looks like the 2D DIC is deviating a lot from the 3D DIC, but it is not. And the evidence is shown here in the R value curves. You will see that they are almost matching. And if you take the average values and you put them in a table, you will get a nice table like this, where we see very, of course, on top of each other in terms of the strength. The uniform ductility will be a little bit different, and the total ductility will be a tiny different, as we've shown earlier. But the other mechanical properties like the N value and the R value are almost on top of each other, which means that the results are really comparable between the different systems with very minimal error, if you were to consider that an error as we compare to the 3D DIC. So let's take another material and we'll go a little bit faster here. This is the steel. This is a very ductile steel with 45% elongation typically. And we did the same exact experiment, we noticed the same thing. When I compare the results, the major strains are almost exactly the same. This is the total ductility of the material, and I'm seeing no difference, or a difference of no more than 0.15% from a 45% material. We still see more deviation in the negative, but as we confirmed it already earlier, it doesn't really affect the outcome of the test, because that difference is deceptive because you're looking at a local measurement at the end of the test. But over the test, the stress strain curves are still on top of each other, and then the R values, which is also important to us, is still repeatable. The summary of the properties confirms that, and you see a little bit of deviations here and there, and that's really good to see. And that's why we try different materials, because different materials respond slightly differently. So I'm going to show one last material with maybe a little bit more deviation than the others, but still it was very reasonable. So you can see here from the strain maps, again, we see like, almost a match when we go to the stress strain curves. Now you can see a little bit of a tiny disparity between the curves towards the end, which is in the fracture zone. And we will come back and address this in an even more important test later on. But just to show you here that for a DP980, the stress strain curves were almost on top of each other. The R values are on top of each other. And even the properties, you see a tiny deviation from one system to the next, but it doesn't really affect the reliability of the data. Let's go and address this issue or this observation. We saw some deviation towards the end, and I'm going to go back to that slide and highlight what I'm talking about. I'm talking about curves that match really good, but then towards the end they show a little bit of deviation. This is related to fracture. And to better understand that, let's go to a fracture test, or a test that represents fracture better than the ISO 6892. This is a special test which is performed on samples usually larger, and I'm using one of our custom samples here. We call it the UT30, and it is essentially a test. So I'm going to play a video. It's a test that's performed just like any other tension test, except that the purpose here is not really to obtain mechanical properties only. The intention here is to identify the point of fracture and then obtain the strains, the local strains around the point of fracture, as you can see in the video here. We like to see 1, 2, 3, 4, 5 millimeter strains or extensometers in order to evaluate the fracture strain in the material. So we did these experiments in a different setup. So we had to change, of course, the measurement volume by playing with our lenses. And so we were able to do this with the two systems that had variable volumes. So that's the 3D commercial DIC system and our 2D DIC system with a single camera and a single lens. So we did this experiment with a couple of materials. And I wanted to show here one of the materials which has extreme ductility. This is about 40%, this is about a 25% ductility material. And the comparison here is just focused on the nominal strains. And you will see the same observation from the ISO 6892 testing, where the nominal strain is very comparable between the 3D system and the 2D system, 2615 to 2594. Very small deviation within about 1% of the value. As for the minor strain, we see a little bit more deviation, but just like we demonstrated earlier, when we put the stress strain curves on top of each other, we see a very good match. And when we go to the R value, we see a very good match. So again, we're confirming the same observation from the standard samples. And what I'm showing here is even if you go to very large samples for fracture testing, the mechanical properties are still fine. Now let's go to the fracture strains. Here I'm showing the same strain maps, and now I'm looking at the strains that are localized around the fracture point. And I'm writing in this table just the 1 millimeter and the 3 millimeter extensometer values, and you will see differences. So let me focus on the 3D DIC. We're seeing about 57% for the 1 millimeter extensometer, while for the 2D DIC, I'm seeing 52. That is a difference of around 10%. So it should be significant. And one could say, okay, that means that there's a significant difference, which means maybe 2D DIC does not really do the job for samples like this, such as large samples or when I'm considering fracture strains. And I would say that is not entirely true. yes, we are seeing a deviation of around 10%. But first, again, let's go look at the perspective from which these tests are performed or why they're performed. These tests are performed to calibrate fracture models. So it's all about fracture, which means first we have to look at the true strains comparison, not the engineering strains, and that drops this deviation to around 7% for the fracture strain of 1 millimeter. And then we go to the main justification for why this doesn't really lead to a significant error as the table shows. These are the two stress strain curves on top of each other. And if you look at them, that difference in the value of the fracture strain of a 1 millimeter extensometer is represented by that tiny deviation between the stress strain curves at the end. And what does that mean? What that means is for those people who use this data to calibrate fracture models, and I'm using here, for example, a gizmo model or a gizmo card, that difference is insignificant in the scope of calibrating a gizmo card. And to show how insignificant it is, I'm going to show our curves that we obtained in this study on the left-hand side, and the curves that are obtained in any typical tension test of that type with repeating the sample 4 or 5 times. You will see that the deviation between a sample and another in terms of fracture behavior is so massive that in the scope of calibrating a gizmo card, those differences that you see from 2D to 3D or from 2D to another 2D are insignificant. And as you go through the calibration process, you see that this does not really make any difference in terms of extracting the parameters. So I'm showing here also another snapshot just for the demonstration of what actually happens during a calibration process for a gizmo card, or when you check for mesh homogenization with finite element simulations, when you try different mesh sizes. You have a lot of scatter around that region, and you usually use a best fit to describe which set of parameters of a gizmo model would work best. And so you can see that there's a lot of room there, that the deviation that you're seeing from a 2D DIC system would fit within it very nicely, and it shouldn't really affect your results that much. So in short, even if you want to use your 2D DIC for obtaining fracture strains, you should still be able to get good results, very good results, without affecting the accuracy of your outcome, basically, in terms of feeding it into a fracture model card. Let's go to other examples of tests now. This test, I'm going to just show one slide about it, because this demonstrates going in the other direction. Now, we went from an ISO 6892 with a field of view of around 100 millimeters to a very large tension sample. So that's a field of view of maybe 200 millimeters. Now we want to go back. We want to go much smaller than 100 millimeters. And this sample is used sometimes for also fracture modeling to look at a localized area of deformation around maybe 20 millimeters by 20 millimeters. Something like this. And I'm showing here a direct comparison for a DP980 between the 3D DIC system and the 2D DIC system. So again, we went back to our systems and we changed the field of view by playing with the lenses and the distance from the camera to the object. And we matched again the pixel resolution with the same cameras. And you can see the results here between the left and the right. The difference between the two was very small. In fact, it was almost negligible for this condition, because there's not a lot of thinning in the plane strain condition. And also because of the pixel resolution here was so much higher. It was closer to 10 microns per pixel, that we were able to get very good reading, whether it's a 3D DIC or a 2D DIC measurement. And just if you are unable to read the 1 millimeter strains, the 3D DIC system generated 41.55, and then the 2D DIC generated 41.56, which is almost a match. Let's go even smaller. Let's go to a shear test. And this is an example of a custom shear sample that we use sometimes. And what I wanted to highlight here is that the area of deformation is even smaller now. The ligament that deforms in a shear test is typically on the order of 3 millimeters max in length. And this video demonstrates a typical shear test. And you can see from this shear test, you have two ligaments that are deforming when we pull the sample. And what we are interested in here is, again, the deformation in each ligament. And we're trying to measure the shear strains in those ligaments, left and right. One of the biggest challenges of this test is, of course, the amount of deformation is usually very large, and it's really difficult to capture even in 3D DIC systems. Sometimes you have a loss of correlation. So therefore, we show this example from a previous project that shows a very nice video of shear deformation in a particular sample. And you can see also on the top right corner of my video, it's an evaluation of the triaxiality. And as you can see, the triaxiality is staying almost close to zero, which guarantees a shear deformation in the sample. Now, let's go back to our systems and recalibrate them for this kind of volume. And you can see now the comparison again between 3D on the left and 2D on the right. This time I wanted to do a comparison at different points in the test. So this is a point somewhere in the middle of the test, and you can see the strain maps here. They look very similar. As for the magnitudes, if you're unable to read the small font, I summarize them here. The 3D system showed a 0.288, and the 2D showed a 0.296, a deviation of around 3%. That's just if we look at the left ligament. When we go to the right ligament, we get a deviation of around 1%. We repeated the same thing. We went to another point on the test, somewhere closer to the top of the stress point or the load. And we noticed the same thing, very similar response between the two systems and deviation within 3%, if not better. And finally, we went to the last frame before failure. No loss of correlation in either one of the two. And the values were almost a match again with a deviation of less than 3%. And so that was fantastic for at least this material. We tried it actually with a couple of different materials and we saw very similar response. But then we want to even emphasize how you could still get very good results with 2D DIC for such a complex test. We go back to the essence of this test. What is this test about? It's about fracture strains and also calibration of gizmo, which means even if you have a deviation of 5, 6, 7% in the actual value of the fracture strain, that does not mean that much deviation when you take this data for the purpose of calibrating your gizmo model. And I'm showing here just the overlay of the load displacement curves and the shear stress strain curves. You can see how they're on top of each other, and that tiny deviation is towards the end, which is literally the same case as when we talked about the UT30 samples. When you carry this over to a gizmo calibration process, it is nothing compared to the deviation that we actually see in the experiments themselves. And this is a sample or an example of a series of tests, shear tests that were performed on the same material, just repeated 4 or 5 times. And you can see just from the raw data, the force displacement data, that we had such a deviation that this would play a much bigger role in defining the accuracy of your gizmo calibration process. So before I conclude my slides, I think we showed you so far a nice story of a comparison between the 3D and 2D DIC. We've shown different types of tests. Yes, all of them are planar tests, but we still focused on 4 tests today, and we showed how the comparison shows really good response from the 2D and the 3D DIC systems, that they're showing very similar results if you're trying to do this in a systematic way and you match your parameters. We still have done more, but we couldn't talk about it because that would open much bigger topics and more information, which we decided that maybe we should push it to another webinar, because there are so many other parameters. One of them is the DIC software. There are so many DIC softwares out there. So for those people who want to consider 2D DIC, the option of processing the data or the options for processing the data are many, numerous. And so this was part of our study, but we decided not to talk about it today because, again, it just diverts the study into a different direction that might be confusing. But we wanted to show you a very simple snapshot. And what we did is basically, we basically borrowed a license from our neighbors here in South Carolina, Correlated Solutions. Their software is the VIC 3D or 2D. We borrowed the 2D license for a couple of weeks, and we used that license to process the same images we got from our 2D system. So this way we have a comparison between the 3D system, the commercial 3D system from GOM with the GOM Correlate professional software, a 2D GOM Correlate software output, and then the correlated solutions VIC2D software. So now you can see there's a nice mix of hardware and software at the same time. And even though maybe it's difficult to read the labels that I put there, I'm going to read just the major strains that were obtained here globally. And you will see from left to right, the 3D DIC system generated 15.02%, while the 2D DIC system with the same software generated 15.02%, perfect match, just like we did in our study today. And then when I change the software, I'm getting 14.95, and a negligible difference for the same images processed by different software. Now again, even though the strain map looks different, that's just a software rendering thing. And if you use a third software, you might get a different render, and that's absolutely fine. What matters at the end of the day is we're showing here that if you do everything sort of nicely and fairly, you should be able to get the same strain signal. And as we showed earlier, if your synchronization with force is correct, you should get a nice match with the force, and therefore the engineering stress strain curve would be also a match. One last parameter that we didn't talk about is going even beyond to much more complex tests. And this is where we wanted to show that you really can use 2D DIC with a bunch of other things. This is one of the most complex tests that we perform in our lab. This is called the tension compression test. And you can see from this nice video on the left-hand side that is playing right now, this is a test where we go back and forth between tension and compression. We cycle it back and forth in one test. We just keep the sequence going up and down until we fatigue the material and break it. And this test, you can see the picture of the setup on the right-hand side. What I wanted to highlight from this picture is that the fact that the sample is so tiny, and we're looking at the side of the sample, not the actual surface of the sample. And we use DIC, of course, to monitor the deformation. And we've done also another comparison with a totally different setup like this one, as shown here in the picture, where we compared 3D measurement with 2D measurement. And this is also the topic of a future webinar, because we wanted to focus on these complex tests with a little bit of diversity from tension or pulling tests to show that you can still see a very good correlation with 2D DIC. And again, this is one of the most demanding tests on our DIC systems because the amount of strain is large usually, and it goes between positive and negative. And you can see here in the video as it's playing that the correlation is not lost, and we are still capturing it with 2D DIC. And hopefully in a future webinar, we will show you an overlay of the two results next to each other to show the limitations of how far you can take this approach of using 2D DIC for complex tests like this. My last slide is just a sum up. What we started with today is an objective. We wanted to show a comparison between 2D and 3D, not just for the sake of comparison. We wanted to compare 2D and 3D DIC systems or approaches for the purpose of answering several questions. Those questions were, how good is or reliable a 2D DIC measurement? And I think we've shown that it's really good. And if done properly, it is as good as a 3D DIC measurement for certain applications and certain tests, of course. And even though certain cases show some deviation from the value that you measure of strain, we try to caution that this is really deceptive. You should go to the outcome of the test and see how does it compare. And we've shown in so many cases that the outcome is almost unaffected. And then we've demonstrated 4, 5, 6 scenarios of different types of tests where you could use a 2D DIC measurement and still get very good results. So I hope answering these questions also provided a general validation for the statement that we can do a lot with DIC without compromising the quality. And we hope this encourages you to start using DIC. If you cannot justify or get a 3D DIC system, it's good to start with 2D DIC system and I am positive that once you start using a 2D DIC system, you will get used to it, you will love it, and you will apply it to other applications that will require a 3D DIC system, and then you can expand to 3D DIC system. This was my last slide. Thank you so much. And please visit our website if you want more information about these tests and others. And for now, I will stop to take any questions, and thank you for listening.
Thank you, Fadi, for that excellent presentation. Before we conclude, we have a few questions from our participants. And the first couple questions are going to be about the setup of a fracture test. And then I hope to have time to get to a couple questions about other applications of this technique. So one attendee wants to know, for evaluating fracture strain, should you include a reference lined near either edge instead of just in the center of the sample?
So Joanne, can you please read the question again?
Yes. They want to know, for evaluating fracture strain, should you include a reference, they said reference lined near either edge instead of just in the center of the sample?
Okay, so maybe this is a specific detail in the test, and to be honest, I am not really sure that I understand the specific question here. So I would like to ask our audience to please send me an email with this particular question or call me, and I'm more than happy to discuss it. I just wanted to also mention something else related to this question. In regards to reference images and lengths, this is something maybe I did not mention in my slides here today, that for every system, whether it's 2D or 3D DIC system, we usually take a reference image with a known scale, and we use that for generating all the data that was shown here. So I omitted to show this earlier in my slides, but just to confirm it, we do take a reference image with a reference length that is known, and we use this in the computation of the different extensometers.
Okay, good. Another attendee wants to know if, does the alignment of the specimen within the grips affect the results differently between 2D and 3D?
Sure. The alignment of the specimen, so now this is regardless whether you're using DIC altogether or not, this will affect your test results significantly. So irrespective of whether you use 2D or 3D, the alignment should be good first. Now, does it really affect the 2D or 3D after that 3D DIC system? It will most certainly affect it, but it should be taken care of in the first place, regardless what DIC system is used.
Okay, good. And another attendee wants to know, when necking occurs, the material shrinks locally. Would that throw off the focus of the cameras, thus impacting the DIC resolution?
Okay, very good question. So the necking, of course, causes a change in depth. However, most of these cameras and lenses, basically, that we use on the cameras, most of the lenses, we set them up so that we have a certain depth of field that is maintained, so that the effect on the resolution is not high. If your application is really sensitive to that, so if a typical lens like the one I use in my 2D DIC system is just a general lens and it works fine. Let's say someone wants higher accuracy and they want to capture this this effect, and they don't want it to affect the results, then you use a telecentric lens like the one that's shown in our slides also by the Spectral system, and that will guarantee you that a telecentric lens is specifically designed for this purpose, so that any change in depth or change in Z is accounted for by a 2D measurement.
Okay, good. And now a question about applications. How about fatigue testing? Do you think this technique could be applied to fatigue testing?
So we showed a very simple, not necessarily a pure fatigue testing, but this video that I showed here of this test is nothing but a tiny version of a fatigue test, because it's just a bunch of cycles up and down. So in essence, the answer is yes. And this is just an example of how it could be done. Of course, fatigue testing is done at much higher frequency with smaller amplitude of load. This test that I'm showing right now here, the video for, is a much lower frequency with a higher amplitude of load. But the principle is exactly the same. It can be done. Of course, you have to just use different types of cameras, higher, basically frame rate cameras or high-speed cameras. But in essence, it can be done the same way.
Okay, good. And I think this will be our last question. This is also related to an application. Can this approach be used to extract strain hardening data? For example, if I carried out a set of tests on a high work hardening stainless steel at various strain rates and then compared the local strain information.
Sure. So I'm going back to this slide in my presentation. This is a CR5. CR5 is basically a mild steel with a ductility of 45% elongation, which is very close to a stainless steel. So this is one of the highest ductility steels out there. Very close to stainless steel. Stainless steel might read 45 to 55% elongation. But we've shown here that first you can get the full stress strain curve, the true stress strain curve, the R values, and in terms of hardening parameters, if you see here in my table the N value is basically the essence of the work hardening parameters, and we got the N value for it here, and you should be able to obtain very good N value for your stainless steel. Even though the N value goes to about 0.4 or 0.45, it should be no problem because we've used the same techniques with other types of steels with 0.3, 0.35, and 0.4 N value. So it should be doable.
Very good. That's great to know. So thank you to everyone who submitted questions. Unfortunately, we don't have time to answer all of the questions we received, but in a few days, all participants will receive an email with further contact information. I encourage you to complete the brief survey that will appear on your screen as you exit the webinar. With your input, we can continue to provide webinars with high-quality practical information that you can use. I also encourage you to follow up with Fadi for more information about how effective is 2D DIC in materials testing. Once again, I'd like to acknowledge the sponsor of today's webinar, Zwick Roel. Zwick Roel, for more than 160 years, has stood for reliable test results, excellent service, and quality and reliability in materials and components testing. For more information, visit www.zwickrowell.com. Thank you again for participating in today's ASM webinar. Have a great day, everybody.